computer. So very quickly, I will show you the okay, so that was the solution to problem number 1. I think, well, most of you, like most of you got it correct. So I was really happy to see the results, okay? I just want you to appreciate one thing. So this is the deflection, okay? There's a deflection, 66 millimeters, and those are the reactions. I just want you to keep in mind for this span, 66 millimeters, that's an excessive amount of deflection, and therefore this member definitely wouldn't work if you were actually designing this member. Does anybody have any questions on the first problem before I move on? We're all good? Because you seem to have done it well, so it seems, okay. So that was the first problem. I'm just going to close this one. And this was the second problem. So like I said, here basically, okay, once you've run the analysis, you'll make sure everything is done and everything else, okay. I strongly recommend that instead of you doing this, instead of going to the view options and, you know, look at your results and look at the Rx, Ry, MZ values, you understand? The problem with the graphics is that you will not see the MZ values, okay? So in other words, you'll see the X and the Y and this, and you know, like I said, but then in order to get that bending moment about the reaction area, the best thing to do is just go and activate your supports, okay? And if you're doing this like on the exam, when you're doing this on the exam, just, you know, click on it, double click on it, so you'll get the same. So here you'll notice it says minus 74.04, but then it shows 74.04 because it means it's going from right to left. And you have a negative, that means it's going from up to down. So you can see even the program does it correctly. Once you put the right direction, you do not put the negative sign. The negative sign is to mathematically show you or how you should interpret in which direction the force is acting. And of course, the MZ, what the program takes as a convention is that if it's positive, it's counterclockwise. So you would show them, in other words, let me just annotate this. Okay, so in other words, on your test paper, all I would want to see is, I want to see the counterclockwise like this. And of course, you give me the value, okay? Now, if you put on your sketch here, you put like all, you know, all forces are in kilonewtons, all moments are in kilonewton meter. As long as you give me what the units are, you can just give me the numerical value, okay? But don't give me the numerical value. Without any units, you'll get 0 for the problem. I'll tell you right now. Okay, because this means absolutely nothing. Are we talking about kips? Are we talking about pounds? Are we talking about kilonewtons? And that's why you got to give me the right unit. Anyways, the units are right there. So that's okay. So that's, I find that that's a way that you don't overlook the fact that you're going to forget to put the bending moment, because whenever the support is fixed, you do have 3 unknowns, and therefore you get three react, or you can get up to 3 reactions. So that's for the reactions, and here were the, and I think all of you got this right. And what I find interesting is you notice that, well, first of all, in the X, they're all going against the direction that the forces are being applied. But what I like about the Y's is that 2 of them go down, 2 of them go up. So it kind of shows you where the building is kind of like being overturned. Okay, so in other words, if these reactions are going down, that means that the building wants to, like if since these reactions go down, that means this part of the building wants to go up and turn over like this. And that's what they mean, that the overturning of the building. Okay, so that's why this is going down, that's going down. And of course, it's overturning somewhere around this, about somewhere around here. And therefore, this is pushing up and that's pushing up. And that's why you have, and then of course, if you take the sum of f, if you take the sum of f of y's, they're supposed to be adding to 0, and they will add to 0. And you take the sum of the x forces, these should add up to the total forces acting in the other direction. And ultimately, the best check is that if I take any point on your structure and I take moments about that point, okay, then if it bounces out to 0, your analysis is perfectly correct. That's the best way to check. Okay, and then of course, so that's for the reactions. And then for, like, if I ask a displacement of this point here, the easiest thing to do is simply activate the node. Okay, so this is how you activate the node here. Okay, and then you simply double click on it, and that's going to give you the deflection. So X is okay? So all I want you to do is say X is 52.3 millimeters, okay? It's positive, so it goes, and then the Y is minus point. So if this is the values you give me on your test, 0.4 millimeters, and you give me 52.3 millimeters, that to me will be perfect, okay? Because I don't go to 2 decimal places when it comes to millimeters. 1 decimal place is more than sufficient in terms of accuracy. And plus, this is still a very close approximation. So that's how you would be able to very quickly find the values of what I'm asking for. And of course, you got to be very careful, make sure your columns are oriented in the right direction, and so on and so on. And of course, and this here, the reason why I ask you for the displacement, I can ask for displacement at this point here or at this point here, whatever it is. That's just for me to quickly check to see if all your members that you put in the member size are correct. And on top of that, if you've oriented them in the right direction, because for example, if the members are in this direction versus like in this direction, well, you can tell right away that the displacements here would be much higher because these are much weaker to resist. So that's why I asked you for those displacements, and just to make sure that you model everything correctly. So overall, you guys did very well on the assignment, except for like I said, Jimmy, you don't just give me the reaction there, you give me all the reactions. Okay, just don't do the just don't do the same mistake on the test. Okay, so now before I move on, did anybody have any problems with this, or is because we're going to be doing like what we're going to be doing today is we're going to just do a couple more different structures. Okay, and the assignment I'm giving you today is basically going to have 5 questions, and are going to be the typical 5 questions you're going to be tested on. Okay, and next week we can go through those questions one by one very slowly, and on top of that, I'll probably have 5 more questions typical. It'll be like a review next week, and then of course the exam we'll have it the week after. So you get a chance to at least try it 2 more times with the assignment as well as with the tutorial next week. So we should be able to get a good handle of this. I'd love it if everybody got perfect on the last exam. That to me would be, I would be ecstatic about that. So hopefully we can all get perfect on the last exam. I would really like that. And that's basically it. So before I close this, if there's no questions, I'm just going to go on and talk about the lecture. So everything's good. Okay, so let me just put this over here. Let me go here. Okay, so basically what we're going to learn today, okay, is, for example, let's call it, how vast of an analysis you can do with ADA. I mean, it's pretty like, guys, we're just like touching the very, very surface of this software, okay? It can do a lot of analysis, a lot of different analysis, as a matter of fact, and so on and so on. So here, what I want to show you is that if ever you are going to be having cables that you want to suspend something from your cables and you want to be able to determine the force in your cables, well, the program will model cables, and the program will also recognize that these are cables, and therefore you don't have to do anything more than just make sure that you specify these members as cables. And then, because most programs, even though these are cables, you'd have put these members in and then you'd have to release them to make sure that you don't transfer the moment. But this program is so, it does recognize cables, and it knows that cables cannot act in compression, and therefore if all of a sudden there's a compression force, it would give you a 0 value, and it's a really good program for that. Okay, so basically what we're like, as a matter of fact, what I did here is that, I don't know if you guys ever did this type of a problem in one of your physics class, but there was years ago, students were telling me that they had this type of a problem in a physics class, and they had to like manually calculate what would be the displacement in the cables and what would be the reactions at the support areas and so on and so on. I said, well, look, I'll show you how you can model this on ADA, and that you'll be able to check whether what you're doing manually, whether you're doing it correctly or not. So it was interesting to see that they found it interesting that they were learning how to do this manually in the physics class, and that they were able to actually just model it very quickly in ADA. and get everything that you wanted. They were able to get the force in the cable, they were able to get the displacement, the elongations, and so on and so on. Okay, so basically here what we have, okay, we have so uh, we have a support here and a support here, and of course we'll consider this has to be pinned and this has to be pinned, otherwise if we put this on a roller it would just slide down. Okay, so in terms of, so it's pinned there and it's pinned there, and on top of that this is a cable and that's a cable, and of course the cable would be the same cable all the way through. And what's happening, you're hanging something that weighs about 12 kips, which is you can appreciate that's 12,000 pounds. So it's a substantial load that you're hanging on that cable there for whatever reason. And now what you're going to do is, of course, okay, so we have, so you calculate the reactions here. Okay, so in other words, what would be the force in that direction, upwards, and so on and so on. Calculate the reactions, and I want to know how much this will displace in the x and y direction based on this amount of load here. And of course, I don't want you to include the self weight. So when I say node A, it's just so you can get an idea of the elongation of these cables. Okay, and this is what we're going to be using. Okay, so these cables will be made with BS19. Okay, that's a type of cable. Okay, and of course this represents the diameter, the ½ inch, because cables are round. This represents the diameter of the cable. So these cables end up being ½ inch, 3/4 of an inch, and so on and so on. And the material is a steel, and it also BS19. And I'll show you where you can find that in ADA. It's under the materials. Now, first thing you do before you rush, okay, before you rush to the ADA, okay, you should establish where you're going to be creating nodes, okay, and it's good to do this in your head to put the coordinates right away, because sometimes you might, okay, you got to remember the coordinate here is you're moving 0 along the X, 8 feet along the Y. Here you're moving at 15 along the X, 0 along the Y, and here you're moving this one here. So this is number 1, this is number 2, and this is number 3. So if you number them this way, you'll know right away which ones you're going to make supports and so on. And then of course this coordinate here is 25, 12. Okay, so I like to do this right away on my paper. So and that's why I don't even have to take out my calculator. If I do take out my calculator, I don't try to do the mental math in my head. I have the value, so when I go to the program, I put the right information in the cells, and I know I can minimize making mistakes. So that's number 1. So once I've decided that, then of course, okay, so once I've decided that, of course, what you do, I'm gonna start a new file. I hope you guys have your ADA open so that we can go through this. And guys, at any time, if I'm going too fast, just tell me to slow down, go back, redo, and I will be more than happy to do so. Okay. So of course, when you open up a new file, okay, this is what you get. And whenever I open up a new file in ADA, I like to go to the file. I like to go to the project configuration, and I like to make sure that I'm working in the right units. So here everything's in imperial, and also the sections are in imperial because I have a ½ inch diameter, so that's good. And at the same time, I like to take off these dialog boxes so that as I'm adding my members, they don't pop up, and I'll decide when I want to add that information. Now, number 2 is, of course, like I said, sometimes it's nice to visually see what you're doing with ADA, and therefore I like to know what the length of the members are. In this case, it's not really a good thing because it's going to actually give you the length from there to there. But so therefore the length would not necessarily, unless you actually calculate this length on your calculator to make sure you put in the right length, you understand? So this 10, 12, this should be 15 anyways. And then of course I put materials and I put the shape so that I made sure I assign the right properties, because without assigning the shapes and the materials, ADA will give you an error message. And a lot of times you might forget to assign one or the other, and therefore you might as well check on your screen that you've done it correctly. Now, in terms of attributes here, I don't have any end conditions that I want to check, but you will see next time I will, okay? And then after that, I appreciate this X and Y, but I know which direction is X, which direction is Y, and I don't like to have that in front of me because sometimes it can be distracting. I simply take it off. And now that I've tweaked my visual options, I'm then of course going to go to structures, I start with my nodes, okay? Now I know I need 3 nodes, so I will add 3 rows to the spreadsheet, okay? And I know the first one's going to be a support node, and the last one's going to be a support node, so I change that right away. Now X is 0, Y is 8. Then the second one, X is 15, Y is 0. And then I look at here and I say, oh, X is 25 and Y is 12. Now, so don't worry if you made a mistake, you know, you can always come back and change these values at any time. You press OK. And of course, there are your 2 supports and your normal node, right? Now, since these 2 supports are exactly the same, I'm going to go to support and I'm going to activate the supports and I'm going to pick them both at the same time. I'm going to right click, go to properties. And of course, what does a pin mean? It means that in the X direction, I don't let it, I fix it in the X direction. I fix it in the Y direction. And of course, I let it rotate freely about the Z axis. So it's got to be free here. So fix free is how I create a pin in ADA. Okay, and if I say okay, now the best way to make sure you've done it correctly, well, if I have 2 yellow arrows and no longer a red dot here, that becomes a pin. If I have 2 yellow arrows and no longer red there, that becomes a pin. So as far as I'm concerned, my reaction areas have been properly modeled. And I can tell you that if you make a mistake here, okay, now if you don't, I didn't try it yet, but if I left it as fixed here also, because these are cables, and because the program knows that you cannot transfer a moment through cables, we might get the same values. I might try it afterwards one day, but I might as well model it properly. But so that's number one. Now, once I've done my nodes, once I've modeled my reaction areas, because I like to do this systematically, because if you overlook to model your reaction areas, your analysis will be completely off, okay? Because it's going to have a completely different effect on the members, and therefore all the internal forces are going to be completely different. And I think that on the last test, there was one person that did not model the supports correctly, and of course, this whole analysis for the beam was incorrect. So, okay, so that's number one. Now, once I'm ready to add members, of course, I activate the members. And then, of course, I want to add members. So therefore, now, like I said, it's up to you to remember where you start and where you end in case you need to, you know, like also look at your results. Because the program, if I click here, that becomes my I node. And if I click there, that becomes my J node. So in other words, as far as this is the beginning of the member, that's the end of the member. And the program will keep that in terms of showing you the results. If ever you want to add a load along the member length, it's going to where you start, where you end. So I just like to remember, like J. So like when I look at my results, I know, okay, where the program is starting to give me the information, okay? 10, 12, I just want to check something. 10 squared plus 12 squared equals second square root equals 15.62. Good. I just checked to make sure the program works correctly. I use, you know, the Pythagoras theorem to calculate the length of that member. And of course, that should be 17.4. Okay, now, once I've added my members, of course, the next thing I want to do is I want to assign the properties. Now, since they both have the same properties, I'm going to pick them both at the same time. Okay, so I pick both of them, right click, go to properties. Now, here I'm going to go slow. So where do you find the information regarding cables? Well, first of all, they're steel, so therefore they would be, you know, you'd find them in the steel section. And you'd have to go down to where it says rectangular and round, okay? Rectangular and round. So in other words, right below that V, okay, the V, you have rectangular and round, and you open up the rectangular and round. And of course, we don't have rectangular members, we're going to have round members. So therefore we open up the round members. And of course, I said these are BS cables. So therefore, like there's RBs, there's GS, BS, okay? Guys, different cables are used for different reasons, okay? Like for example, cranes have one type of cable, elevators have another type of cable, and so on and so on. And it's, I guess it's a question of how many strands you have to make the cables, which, and then how more flexible and how strong is the steel. So this here, we said it was a BS, so therefore I will go to the BS, okay? Open that one up, and I said it was 19, so therefore BS 19. And here you see it. So therefore, the 1/2 inch is the smallest diameter cable that you get in the BS series, and then after that, it keeps going up by 1/16 of an inch, all the way up to an inch. So they make cables that are an inch, a 1/2 inch diameter, all the way up to an inch in diameter. And therefore, that's the one I'm going to choose. So like I said, you go to rectangle and rectangles and round, and then in here you pick round, and then you pick which group that cable would belong to. Is it an RB? This is round bars, I believe. So if ever you're using round bars, this is where you would come and use the round bars. And then of course, these are the two different grades of cable. So that's okay. And of course, now, if you ever want to see what the properties are of this thing, right, it just shows you that it's a circle, okay, and it tells you what the moment of inertia is. I mean, not the moment of inertia, it tells you what the section modulus, the radius of gyration. And here, I like this. It gives you the moment of inertia as 0 because it recognizes a cable, so therefore, it will never transfer any moment. And I like the way the program does that. So you guys don't appreciate this, but I do. When I had to learn these programs, we had to learn how the thing actually, was programmed and how the subroutines were put together and so on and so on. So that's basically, that's for the member. Press OK. Now, as far as the material goes, well, we know that it's a steel cable, and we know that they're under cables. And I said that it was a BS19. So there you go. Okay, so simply double click on materials. Now, we're not going to include the self weight here, but you should always activate the dead load. I mean, the way you can exclude it is just don't put it into your load combinations, okay? And we're basically done. Now, we don't have to do anything here because it's a cable. We don't have to release anything. It's a cable. If had it been steel bars, we would have to release one side because you might be on steel bars, you can transfer things if you weld them together. So you don't have to release anything. You press OK. So here we go, 17 feet. So the member designation is there. The material is there. My size is there. Everything is there. I'm happy. And therefore, that information is pretty well been verified. I can take that off, and therefore I can take that out of my thing. Now, once I've modeled everything, I'm happy. In other words, the members have been designated properly, the materials have been designated properly, the reaction area has been designated properly. The geometry, first of all, is good. In other words, the dimensions work out. Now I'm ready to move on to my loads, and therefore I will go to the loads. And of course, I worry about my load cases. Now this here is very simple because we're always going to have one load case. So therefore, but in theory, when you're doing a structure, you'll have dead loads, you'll have live loads, you'll have wind loads, and therefore you'll have different load cases. And then you should just worry about putting all your load cases into the program. And then once all your load cases, then you can go and tell the program how you're going to be combining all these loads. And that you're going to learn next year in your design courses. So right now I'm just worried about load case, and I'm going to define the load case. Okay. Now, don't generate it because the program can generate all the load case that's required by the National Building Code, and that's way too much. Now, this is the dead load that the program uses to calculate the self weight of whatever you're modeling. And of course, now here you can call it, call it a live load, call it a gravity load. You don't have to define it. The program will not give you an error if you don't define it. But if you do define it and you ask the program to automatically generate the load combination, well, there is a National Building Code, different load combinations of live loads, dead loads, wind loads, snow loads, and the program will generate all of those for you if you want. So I'm not even going to define it so you can save some time. So I'm going to press OK. So once I've created my load case and cases, okay, what I do is I activate the load case, okay? And of course, as soon as you hit that, it tells you what do you want to see. I want to activate my live. I'm going to save the project, yes. Okay, so yeah, save it there. I don't care. Now, so now I'm ready to apply the load. So since the load is being applied right at this node, well, I know that I'll simply go and activate the node, right? I will activate the node and I will pick the node, double click on it, and of course, this is what pops up. Now, I have a force that's acting in the y direction, it's acting downwards, so therefore it would be minus for downwards. And of course, the magnitude of that force is 12 kips. And if you don't see kips here, you know you can right click and you can change your unit. So if you have pounds for whatever reason, you can right click and change it to kips. Don't do the math in your head. Let the program, you know, do the math. Press OK. And of course, there you go. So there's the 12 kips, okay, and it shows you as negative. That means you're putting it downwards, okay. And that's basically it. It's that simple because we have nothing else that we need to add here. And therefore now I can go back to my load, go to my load combination and tell the program how I want to combine my loads. And of course here, I'm going to call it, you know, live or whatever, a live load. And then after here, this is the one load combination. I will activate which load case I want to be. I'm just a live load. Now, I will not talk about envelopes because that's a whole new animal. Clear the drawing, and that's basically it. So did my modeling, put in my load cases, told the program how to combine those different load cases, and now I'm ready to run the analysis. So therefore, okay. Now, like I said, you can run it from here for your static analysis. You can also go here, analysis, and you know, it's up to you, whichever way you want to do it. You know, sometimes I find that when programs offer you too many options, it's more confusing than anything else. So I'm ready to analyze. And of course, as soon as I see calculations complete, you may consult your results. Great, I didn't get an error message. And I can close this. And now, of course, if I want to see my reactions, of course, I would go here. Okay, see my reaction. So therefore, I will go to results. And of course, I should have reactions both in the X and in the Y. I will not have anything in the Z, but you know, just to, those are the only directions I should get in some reactions. And and I say apply, okay. And of course, I need to activate which one I want to see, and there you go, okay. So there are the reactions, okay. There are the reactions, and therefore here, and then of course, if I want to see the values, okay, I can also have gone here, activate the support, double click on them. And it's going to tell me, well, minus 6.92 kips in the X direction, 3.69 kips in the Y direction, okay. And of course, that's for that one. And then of course, for this one here, I can simply go and if I, you know, and therefore Rx is 0.962 direction. Okay, and if you notice that the sum of f of y of f of x is equal to 0, and that's what it should be. Okay, and of course you have no moments. So now if you take this and this, the sum of f of x is 0. If I take 3.69 plus 8.31, that should equal 12. 12 upwards is equal to 12 downwards. The sum of f of y is 0. So far my analysis is perfect. Okay. Now if I want to see what kind of tension force, okay, find the axial force in kips. Now, what I like about this is that you can do this. Okay, you can look at it graphically. I personally don't like to look at it graphically, but if you want to see, this is where you activate the axial force. NZ is the axial force in a member. Okay, so if ever you're looking at trusses, if ever you're looking at any axial force, that's where you'll find it. You can say apply. Okay, so there you go. So in other words, now you're looking at this and you say, what is this? Well, this means that it's positive. That means that you have a tensile force in here that's stretching this cable, and it's got a value of 7.85 kips in this member here. This one has an axial force, in other words, a tensile force because it's positive. It's got a value of 10.81 kips, okay? And of course, if ever you want to see it by individual members, that's the way I like to see my results. I simply double click on the member. I'm sorry, I have to activate my member. I can double click on the member. Now, if you see bending moment 0, if you see shear is 0, that means you've modeled correctly because you're only supposed to have axial force in the cable. You're not supposed to have any bending moments, not supposed to have any shears whatsoever. And you see here that it's consistent and it's a positive value, and therefore you have a tensile force. Now, this tells you the deflection right here, okay? The strong axis deflection. But I don't want to see that. What I want to see is, for example, if I want to know the displacement of this node, I activate the nodes, I double click on it, and then it's going to tell me that the displacement in the X is positive, so therefore it's in this direction here, positive, and it's 0.09 inches, okay? And if displacement in the Y is negative, so therefore it's downwards, and it's 0.89 inches. And there you go. Now, if you want to see, of course, if you want to see how this thing is displacing laterally, okay, you just take this squared plus this squared, take the square root, it's going to tell you what the displacement is laterally, okay? So that's if you want to, but I like to see the displacements in the X and Y. Now, mouse, okay. Now, like I said, if you do this and you say, well, give me the deflection in the strong axis, apply, okay. Well, it just tells you how much this has elongated and how much that has elongated. It doesn't give you the displacement. So if you want to know the elongation in the cables, there you go, okay. And that tells you that this thing has elongated 0.74 inches, okay, and this one has elongated 0.63 inches, okay. That's the deflection. You'll get the elongation. You won't get the displacement of the point. So if you want to know the elongation, well, you ask for the deflection. And like I said, in the old days when they were doing this in the physics class, they take about an hour to try to calculate the reactions and calculate the axial force, and then they would try to calculate the elongation. And with ADA, once you model it and you make sure you model it correctly and you put in the right properties and everything else, you get the values, all your values, right after you run your analysis. Is this clear to everybody? Did everybody get the same results, or is?
Yeah, I got the same thing.
The same thing? Good. Okay. I mean, good. Now I'm gonna be sending you this PDF. Like on this PDF, you'll have the step by step. Okay, okay. And of course, like, so you'll be getting this, not PDF, this PowerPoint, I should say. So it's all written here. You're saying, of course, run the analysis and look at the analysis. So the only thing I don't do on the PowerPoint to explain to you how to look at your analysis. And of course, the most important thing is that after you've modeled everything correctly and after you applied your loads correctly and after you've done everything correctly, the nice thing about it is what do these things mean to you, okay? So for example, if ever I would be designing the support here, if this had to be anchored to the wall, I would have to make sure that it's able to resist a pullout of 6.92 kips. So the anchor here that I would put into whatever needs to be, it has to be able to resist at least 6.92 kips of force before it pulls out this way. And then in terms of shear, because it's going this way. So this is what's nice about this. The program gives you a lot of information that helps you to be able to design these support areas and so on and so on. And of course, I would go into a catalog, find different type of anchors, see if the pullout is greater than 6.92 kips, and that's what I would use to start supporting my this cable that has to support this load of 12 kips. Okay, so that's like I said, that like if you need to design cables, and what I like about the program is that if ever using cables as bracing in your frame, because it's a cable, it will never be able to take a compression force and it will totally disregard in the analysis. That's how powerful this program is, okay? So before I move on to the second example, is everybody okay with this? Any questions? Does everybody understand what an axial force is? You know, that to me is important because it almost looks like, does everybody understand what an axial force is? Or who doesn't understand what an axial force is? Don't be shy, guys. Now's the time to ask, because it's pretty embarrassing. We're going through all of this and you don't even understand the basic concept of what we're trying to do in terms of figuring out what the internal forces are that the external forces will create in the individual members.
Can you explain it again?
You want me to explain
What
again
parts?
what an axial force is?
Yeah, just to make sure.
Okay.
Internal force.
Okay. An axial force, just to make sure. Okay. So basically, when you have a member like this, okay, basically, you know, for example, here's my member and I'm supporting here and I'm supporting here. Okay. So now if this is my member and I put a load here, okay, so therefore this member can bend. Okay. This member can bend, this member can shear. Okay. And so on. So now, when it comes to forces acting in the longitudinal direction of the member, these are called axial forces. Okay, and these axial forces can do two things. They'll either, if this is my, like for example, if this is my member here, okay, these axial forces acting along the members can either push the member together, and that's going to cause compression. So in other words, all the fibers are going to be pushed together. Or these axial forces can do this. They can pull on the member this way, and therefore this will cause tension. Okay. Now here, when I put a force like this, okay, what's happening is that in order to resist that force, these members are pulling this way, or you know, so, and therefore what's happening is that you have tension here. Okay. So in other words, the member, like these members are all being pulled together, and therefore you get the way the program tells you that the fibers are in tension is because it gives you a positive value there. That's what the positive value means. It's just, this is to tell you right away, oh, all my fibers are being stretched. Okay, and since steel is being stretched, very good. That's how steel likes to be. That's how steel is the best way that it can be served, is by always having it act in tension. So this is what this means. So therefore, and then when I see this, the same thing. In other words, this thing is pulling here, therefore all the fibers are being stretched, okay? And therefore, and it's telling me how much of a force is developing in this member here, okay? And therefore, based on that force that's in that member, I can even determine, for example, at what point it will break, okay? So for example, if I know the tensile resistance, okay, the tensile resistance of the steel is, for example, if I say, like, this is hypothetically, okay, but let's say the tensile resistance of the steel was 10 kips right now, okay? This is very low. I'm just exaggerating, okay? And all of a sudden the force here is 10.81 kips. What's going to happen to the cable?
Is it going to break?
It's going to stretch, it's going to start yielding, and then of course if you hit the ultimate tensile strength, it's going to break. Exactly. So that's what these things tell you. They tell you that these are the forces that are going to develop in the member, okay, and therefore that's what the analysis does. And then the resistance of the member, well, that you determine based on whatever member you're using. If it's a steel cable, if it's a steel beam, if it's a wooden beam, if it's a wooden cable, I mean a wood, steel, okay, concrete, and so on. And therefore, once you're able to determine how much forces are, or what kind of force and how much, and the value of those forces that your structure is being subjected to, then you can evaluate the materials that you're using and the size of the materials you're using. Would they be able to resist those forces? And that you'll learn all in the design course. So that's what you're actually doing. So this here, okay, so for example, if all of a sudden I found out that this cable has a tensile resistance of, let's say 70,000, okay, 70,000 pounds, right? Well, I know that 70,000 pounds is way, or that's 70 kips. So I know that 70 kips is 7 times stronger than there. Therefore, it would be very safe for me to put a load of 12 kips here, because it's never going to break the cable, because the cable can resist up to 70 kips. And that's what's nice about analysis. And that's what's, and where do I get the resistance of this cable? Well, the cable manufacturer is going to tell me for this diameter, this is going to be the breaking point. Okay, so there I get that information, or I can actually calculate it based on the strength of the steel, based on the diameter. Okay, so that's another. Okay, but what I'm saying is that without knowing what these forces are, even though you know that the resistance of whatever the cable is, you're not even sure if it's going to be able to hold it or not. But once you do your analysis and you know what the forces are that develop in the member, then you can determine and tell people, yes, it's safe. You can hang it there. It's not going to fall. Okay. And that's what an axial force is. So it either stretches, it's always acting, like in other words, it's always acting in the longitudinal direction of the member. In other words, it's always acting across, like for example, like if you're looking at this cable here like this, okay, it's acting in this direction here, okay. In other words, it's acting in the longitudinal direction of the member. And if it's pushing the fibers together, it's in compression. If it's stretching the fibers, it's in tension. And that's how, and that's why it's very important to know whether it's tension or compression, because if the material is acting in compression, it has a certain resistance, and in tension, it has another resistance. They don't behave the same way, whether they're being subjected to tension or compression, okay? And steel loves to be in tension, okay? And that's why if you can, you always subject the steel to tensile forces. And just for your general information, okay, the nice thing about when you're designing a suspended bridge, okay, and you have your cables here, the beauty about this bridge was is that it was made with steel cables, okay, and here's, of course, here's your steel deck. Well, the beauty about this is that the whole top cable of the suspended bridge was all in tension, and not only that, all the hangers that they used to support the bridge deck, these were also all in tension. So that was the best way. And then what they used to do is they used to make big masonry. If you look at the Brooklyn Bridge, okay, they would make this either out of masonry or out of concrete, okay, and concrete loves to be in compression. So you're using the right material here for how it's going to be subjected to the forces, and concrete loves compression, and you're using all the material here in tension, and steel loves to be in tension. So that was one of the big advantages of the suspended bridges, is that it really used the materials in the right direction. If you guys, I don't know if you guys know about the Brooklyn Bridge, the one that's like that connects Manhattan with Brooklyn, okay? Well, if you ever look at it, okay, it's a beautiful bridge. This was built in 1836, okay? And if you look at it, you'll see that the two piers here are made out of masonry, and masonry is great in compression, and then everything else. And of course, that's the beauty of that design, and that's what allowed, for example, the Golden Gate Bridge to, to span 4,000 feet. These things are starting to, like a 4,000-foot span, which was amazing. And that was a nice thing about steel, is that we were able to get longer and longer spans, and therefore being able to cross wider and wider rivers because of the fact that we were able to, set the piers at a depth that was reasonable, and therefore we'd be able to, you know, we'd be able to literally walk. Not only, what I love about bridges is that not only do you walk over water, but you actually walk over air, which is amazing. You understand? So a bridge for me is, it's for me, a bridge is land over air. You understand? I can walk over the air because of the bridge, and that's what's really amazing. Okay, so that's axial forces. Okay, and like I said, bending forces. Well, that's what happens when you have a bending force. Well, what happens in that case? Okay, this is in tension, this is in compression, this is in tension, and therefore the fibers here act differently, and so on and so on. And a shear force, again, different, different way it's going to act on the fibers, and and therefore bending resistance, shear resistance, tensile resistance, compression resistance. This is all going to depend whether those forces are present, and if you have to evaluate for them. That's all it is. Okay, now, uh, okay, so now we'll go on to another. So I'll open up okay, so now another thing I want you to realize is that, okay, this looks simple for me, but I realize that people make the same mistake year after year. First of all, let me start a new file here. I'm going to start a new file. Okay, and we'll now here, okay, these things are they're basically called pin structures. Okay, in other words, everything is pinned except, guys, okay, Everything is pinned. Okay, so in other words, you have a pin support here, pin support here, and you have. But the thing is that this member here is pinned there. This member here is pinned there, and this member here is pinned there, and this member here is pinned there. So it's what we mean by, so in other words, these braces here, okay, these braces here, or these diagonals, I should call them, that connect these two things. Now, where do you see these things? Well, this is very popular. For example, utility companies, whether it's electrical companies and so on, they want to hang a wire. Okay, they want to hang a wire somewhere, and therefore and they have to turn, for example, like this is the direction of the wire, and then they're turning, and therefore they're going to have to be able to hold that back here, and therefore they put up this. Next time you go along the highway, you might see these along the highways where you have these cables. Okay, so this is a very typical structure that you use to be able to suspend wires and so on. Okay, and now what I want you to realize is that in ADA, this is a continuous member. Okay, this is a continuous member, and this is a continuous member. But this, in order for you to model this correctly in ADA, even though this is one piece of a beam or of a pole or whatever, okay, in ADA you would have to create one member here, and you'd have to create another member here. So even though this is continuous, and it will actually come to the site in one piece, when you want to model it, you have to model as if this goes from here to here, and then from there to there, so that this member here can interact with that member. If you don't create a node there, then the program will not be able to have this member, okay, interact with that member. And that's what that node does. Okay, here it's pretty obvious. Okay, the member goes from there to there, and therefore, but here it's not that obvious. So here what happens is that even though this looks like in other words, what I've seen people do is they create a node there. Okay, they create a node here, and they create a node there, and then when they go add their member, they add the member from there, and they go right up there. Well, that's wrong. You need to create one member, two members, and then you leave the members as if they're welded together, as if it's plus, 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 and then by creating that node there, you can have this member interact with that member, and the analysis will be done correctly. And then on top of that, these diagonal members are pin connected to these members. They're not fixed. If they are fixed, then you can model them as being fixed. And by default, when you add this member, the program will fix this member to that member, and we'll have to go and release it, just like we did for the beams, for the smooth pins. That's just to give you an overview of what we're doing. Okay. So basically here, like again, before I rush to the program, I start establishing. This is one node. This is two nodes. This is three nodes. This is four nodes. This is five nodes. Okay, so that's the first thing I worry about. Where am I going to be? And of course, so 1 and 4 are going to be support nodes. 2, 3, and 5 are going to be normal nodes. And of course, what's the coordinate here? This is 0, 6. This one is 0, 12. This one is 12, 0. And this one is, of course, 12, 9. So by doing this on my sheet of paper, and if I have to do some, if I don't want to do the mental math, I literally have my little calculator next to me. I know 6 plus 6 is 12. But if all of a sudden I get to I have another one up here. So it starts being 6 plus 7 plus 8. Instead of doing that in my head, I do that in my calculator, and I put the coordinate. And that's why I like to put everything on my sketch, because the program is just input, input, input. So if you know what you're going to be inputting, work it out on your paper, and then just go to the program and input it. Okay. And everybody rushes to the program without doing this very simple thing. So not right away, I know that when I go to my spreadsheet for my nodes, I'm going to be adding 5 lines. I won't have to guess that. I know, and so on and so on. Okay. So there you go. So that's number 1. Okay. Now here it says calculate the reaction, the displacement in inches in the direction, in the XY direction. Okay. So I want you to calculate the reactions here. And I want you to give me the displacement at this point here. Okay. And of course, if you're actually designing this, then we can go look at what are the forces in these members. Here, of course, we'll have some axial forces. Here, we're going to not only have, we're going to get some bending. Okay, we can go look at that afterwards. But right now, I just want you to be able to model this properly. Okay, and on top of that, the strong axis of the column is perpendicular to the lateral load. So remember, When you're looking at steel, okay, the strong axis is the one that is parallel to the flanges, okay, and that in steel we call that the XX axis. So therefore, you want to make sure that the flanges are perpendicular. In other words, when this is the load here, you want to make sure the flanges are perpendicular to the direction of the load, and that's where you mean by putting, because this thing is about at least twice as strong as in the YY direction. And if I what I'm going to do, I'm going to do it correctly, so we all know how to do it properly. But after that, I can go back and put it back the way it was, just to show you how, what big difference that would make in terms of the displacements. Okay, and that's why. So now we're going to go, and of course, so everybody started a new file, I hope. And what we're going to do is now go, of course. Sorry, I have this in my way here. File, project configuration. Now, of course, because my last model was an Imperial, by default, it's still an Imperial. So I don't have to change anything here, but it's always good to make sure I am an Imperial. And of course, remove these dialog boxes because I don't want these to pop up. And as far as the analysis goes, more than ample. Okay, 10 segments of 10 and so on and so on. Of course, I want a linear analysis. Okay. Guys, this is amazing. It even does non-linear analysis, okay? I don't want to get into this, but non-linear analysis is like doing an analytical load test to a structure, okay? And analysis with releases. So, like I'm telling you, this is a very, very powerful software when it comes to analysis, okay? And it does moving loads, it does 3D analysis, and so on and so on. It does dynamic analysis. That's what this is, okay? This is your dynamic analysis. It's a very strong, and it also does design if you want. So now I'm happy with that. And of course, like I said, I always like to, as I'm going along. So now in this case here, I'm going to do three things. I'm going to want to see the length of my members. I want to see the material. I want to see the shape. That's number one. Since I want to see in which orientation the in which orientation the flanges are going to be, I'm going to want to see it in 3D. That's for sure. I also want to make sure I release the members correctly so I can create a pin connection between the members. I want to see the end conditions. So this is all things that I know now, if I forget to do this, I just come back to my visual options or type in the letter O and I come back and I select these. And of course, like I said, I love the fact that it gives me the X and Y, but I don't like to see that on the screen. I find it a little bit distracting. I press apply and okay. So now that I'm ready to go, okay, so I'm ready to go. And of course, go to structures, go to nodes. And like I said, since I've already established I'm going to be needing 5, I right away 1, 2, 3, 4, 5. Okay. And I know number 1 and number 4 are going to be my support nodes. So I don't forget to do that right away. So that's what's nice about having everything on my sketch. I don't have to break my head. Now, the first one is always going to be at 0, 0. The second one is at 0, 6. The next one is 0, 12. Then after that, we are at 12, 0. And then after that, we are at 12, 9. Okay. And as you know, if you made a mistake, don't worry. You just come back and correct your spreadsheet. Okay. So far, so good. And now I press OK. And this is what I see. Fantastic. Okay. Now here, like before, I definitely want to release, because this is fixed. I see a red dot here. I see a red dot there. So I want to release that. Therefore, and since they're both pinned, I'll do them both at the same time. So I'll pick both. I'm sorry. And I'll put properties, okay? And therefore, like I said, what's means I will not allow any displacement in the X. I will not allow any displacement in the Y, but I will allow it to rotate about the Z axis. And I now created 2 pin supports, okay? So since they're both the same, I did them both at the same time, but if one was a pin, one was a roller, I would do them individually. So now I've got my nodes, okay, I've got my nodes and I've got my supports. So the next thing I want to do is I want to add my members, okay? So I'm going to add members. So I'm going to go from there to there, from there to there, Okay. Then I'm going to go from there to there, and then I'm going to go from there to there, and then I'm going to go from there to there. Okay, so there you go. So now I've added my members. I check my diagram. This is 9 feet. That's 6 feet. That's 6 feet. Well, I don't know what this is because I would have to do the trig. Okay, but I'm assuming that this is correct. So as far as I'm concerned, the geometry so far looks good. That means I placed my nodes properly. Now, because I have two designations, I have one designation for the columns and I have one designation for the braces. Okay, I will start with the columns and I will assign the properties to the columns. Okay, so I pick one, hold down the control button, pick the other one, and hold on, or okay, that's one way to do it. Otherwise, I could have picked these two at the same time and then hold down the control button as you wish. But just if when you want to keep adding, just hold on the control button. Now, we have picked all the vertical members. Therefore, I right click, go to properties, and we go to, we said that these are W8 by 15. So therefore, we're going to go to steel. And we know that the W shapes are all under this W. Oops, W. So W's. Now, this is imperial. Of course, that means this is an 8-inch, has a depth of 8 inches. W8 by 15. So I will go under the W8 here and look for 15 pounds per foot. And there we go. Okay. Now, if I want to see the sectional properties or the, okay, there it tells me exactly what, this is. So in other words, it has a depth of exactly 8.11 inches, the flange width and so on. If I wanted to know that information, press OK. And I will press OK. Now, as far as the materials goes, I can do it right now. I'll do it, since it's all the same type of steel, I will do that all at the end. So that's number one, press OK. And now you see that, okay, I'm not sure in which direction the flanges are, but it looks like the flanges are not perpendicular to the load. So I'm going to have to go and fix that, okay? But before I go and place the members in the right thing, I like to finish assigning my properties to my members. Now I'm going to go pick the two diagonals, okay? Right click, properties. And we said the diagonals were W6 by 15. So we know that we're in the W sections, white flange sections for the W. W12, so they're very small, 6 inches, which is not a very big one. You see it can go down to 4 inches. Here's a 6, W6, W6 by 15. So here's a W6 by 15. Okay. Now, the other thing is that I'm going to do this right now. Okay. The other thing is that I know that this member is pin connected here, pin connected there, pin connected there, pin connected there. So therefore, I'm going to release it. And the way I release it right now, it's fixed, fixed. Plus, plus means fixed, fixed. That means it's welded, 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 released, released, welded. And of course, I'm releasing at both ends, and therefore I would pick that one. I press OK. And this is how I can tell I've released it, because I asked the program, if you remember under visual graphics here, I asked for attributes, I asked for end conditions, and therefore by seeing a circle there, I know that I have released that member from that member, I have released that member from that member, and of course they're going to be released from each other. So that's number one. Now, the last thing I want to do is, of course, assign the material, since they're all the same thing, so I will pick them all at the same time. Right click, go to properties, and now I'm just going to go and assign the material. And we know that it's steel. Now, oh, where's the material? It's steel, and I'm telling you that it's a G, I'm telling you it's a Canadian steel, which is G4021. So G4021 and 350W, which is what we used to produce in Canada. And of course, you might as well activate the dead load, but we're not going to be applying the dead load, but in case eventually you want to do it. And okay, so now, so everything looks good. I'm going to go remove all that information. The length, the shape. Oh, no, I'll leave the shape. I'll just take out the length and the materials. Okay, so therefore W8 by 16 by 15, everything looks good here. Now, like we did last week, okay, we want to see in which direction, okay, we want to see in which direction is the axis been placed, and by default, okay, the program is placed it a certain way. So if you remember last week, what we did, we went to the camera here, okay, at the bottom row of the top ribbon, okay, we went to camera right next to it. There's that little triangle that you can pull out, pull down menu. And of course, I like to see an isometric view. And there you go. So if you come here, okay, you'll notice that the flanges are not perpendicular to the load because the load is supposed to be is being applied. The load is being applied like this, and these flanges should be perpendicular to the load. Okay, so all we need to do now is, of course, rotate them. Okay, now these have been applied properly. In other words, they always put okay. So what we need to do is rotate these. Okay, so clear the drawing. Now, I need to know what node that I'm rotating about. Now, I know that this was node 1 and node 4 because I created that way. But if you don't remember your nodes are, you go to your visual graphics, you go to elements, and you say, look, these are nodes, give me the numbers so I can see them on the screen, apply. And that's why the graph would have told me right away that that was node number 1, node number 4, because that's the way I've actually, so therefore I put it here anyway if I don't remember. So I get to my node numbers. Now, I will rotate this one. Oops. This and this. Okay. So I pick the two members that I'm going to be rotating simultaneously. And of course, I go like we did last week. You go on the vertical bar near the bottom. You'll see that little circle with the arrowhead, which is a rotation. And it's the pop-up menu. And of course, I want to turn it to 0 degrees. And then the node that it's being rotated about, well, node number 1, press OK. And there you go. So now I've put the rotation and the beam, the flanges are exactly perpendicular to the way, and therefore I put the strong axes perpendicular to the load. Now I do the same thing for the other side. Go to rotate. And again, I'm going to rotate it by turn it 90 degrees, or in other words, it was at 90 degrees. I'm going to rotate it. And then, of course, it's rotated about node number 4. Press OK. And there you go. So now that my model is pretty well finished, in other words, I made sure the members were assigned, the geometry is good, the end conditions have been modeled properly, the axes have been rotated in the right direction, my model is pretty well complete. Now, if you want, you can leave like this. I don't like to work with this because when I want to go look at my results, I like to look at it very simply. So what I'm going to do is, of course, I'm going to go back here and I say, well, I don't need to see this in 3D anymore. So I'm going to take off the 3D. I really don't need to see the end conditions anymore. I can leave those on. Those are less irritating, okay? And I don't need to see the shapes anymore. And I don't need to see the numbers anymore. Apply, and everything's gone. Now, the other thing is that I don't like to see this view. So I like to go back and put right view. And that's exactly the view that we had when we started off the program. Now, the program by default opens up a right view. And this way I can look at it and it's in the same direction. Okay, and that's what I like to look at. But guys, you can leave it in 3D, you can leave it in isometric. It's up to you. I like to work this way. This is my fetish. It's not a requirement. This is just personal preferences. Now, I know that my model is complete. Everything's been done. In other words, rotation of the axes, of the strong axes, end conditions, member sizes, and everything else, and the designation. Now I'm ready to go and apply my loads. So what I'm going to do is, of course, go to loads, load cases. I'm going to define a load case. Now I'm just going to call this lateral load. Now this lateral load, believe it or not, can be actually caused by the cable itself. Okay, as a matter of fact, I've done this in my career where I had to design these structures, and believe it or not, the electrical engineer would actually give me what would be the forces that these cables would impose on my structure, and I'd have to design my structure accordingly. Okay, and this is all given to you by the guys that actually manufacture the wire. So that would be a lateral load. Now, of course, if I want to apply loads, I have to activate my load. So I'm going to activate the lateral loads. Yes. Sounds good to me. Save it there. I don't care. Now, since the loads are being applied at my nodes, then I know that I can go and activate my nodes. And I mean, I could have gone to the member here, okay, and activated, but why? Like, it's much faster if I simply activate my nodes. Now here, I'm gonna apply the at this node here. So I'm gonna double click. And of course, it's in the X direction. So therefore it would be FX, and it's going from left to right. Therefore it would be positive. So therefore I'm gonna, and of course the units are correct. So there's 10 right there. Press OK. And now here, I'm going to double click on that node. And of course, again, it's positive. So, and it's in the X direction. I'm going to be putting here 12 kips. Okay. And there you go. So now both my lateral loads have been applied to my structure. There's nothing else to do here. So all I need to do now is tell the computer, what do I want to do I want the dead loads? I always run my analysis once without my dead loads so that I can do a quick check to see if everything looks good. In other words, the sum of my reactions and so on and so on. And then ultimately, when I'm actually going to be doing my analysis, I'm going to, of course, include the dead load. But right now, I'm going to run it without the dead load. So I'm going to go to load. I'm going to create a load combination. Okay. Define. Okay, so now I'm going to call this, lateral. And then, like I said, in reality, what I would do, okay, and then if anything, I would consider lateral plus dead. Okay, so there I would have one. Now I would include all my lateral and all the self weight of the members. So therefore, that's how I would have two different load combinations. But and of course now I'm ready to. Okay, so here, like you'll see there. Okay. I forgot to, okay, so let me go back to my load combinations. I shouldn't have pressed OK. I apologize for that. Definitions. Okay, so now I'm going to go to here I'm going to define my lateral load. So the first one is just going to be the lateral load. The second one is going to be, I'm sorry, I don't need this, so I'm going to delete that. Now this one here, once I run the first analysis, I don't have to rerun it. The program is going to run both of them for me simultaneously. So the first one is going to be my lateral load, and my second one is going to be my dead load. So now I'm including one analysis, okay? And then of course, these are going to be different factors when you're actually designing. You have different values in here, but I'm going to leave everything at 1 right now. Press OK. So now I'm ready to run my analysis. So therefore I say run the analysis, save project, yes, analyze. And the program has analyzed all your load combinations. So press close. Now I just want to see the lateral loads, okay? Don't do this during the test, guys, because you might pick the wrong one and you're going to give me the wrong values and I'll think you've done it incorrectly. So this is just to show you that in reality, you can, you always, have your load cases, then you do your load combination and you combine them for what you need to do your analysis for. And now I'm ready to look at my reactions. Okay, so basically, if I want to see my reactions, of course, I can either activate my reactions here and I can double click on this here. Okay, it's going to say Rx is minus 22 kips, so therefore it's 22 kips going from right to left. Ry is minus 19 kips, that means it's going downwards. And of course, dz should be 0 because it's a pin connection, that's okay. And of course, if I want to see this one, the same thing. Okay, like I said, when you put your values, guys, if it happens to be a fixed reaction, I don't recommend you look at it graphically. You're gonna 9 times out of 10 people always forget the moments. And I think who did that last for the assignment? Who forgot the moments? I don't remember, but I know somebody forgot to indicate the moment, and that's because they were only reading. Ariane, I think it was you. Am I correct? On your assignment, you forgot to show the moments, and I wanted to highlight that.
I placed my moment, sir.
On your assignment, you did? Somebody forgot to put the moments. I don't remember who, but somebody last week. And that's the mistake they make. Because,
It may be me.
pardon?
It may be me.
I know somebody forgot to put the moments, and I'm telling you, don't do that mistake because you're definitely gonna get penalized for it. Okay, so there you go. So, and then of course, if you want to see them graphically, in this case, you can because you just have X and Y. Therefore, you go to results, the X and the Y. Rx, don't forget to put the numerical value, Ry. What's nice about seeing them graphically, at least you won't screw up on the direction. The program puts them in the right direction. And of course, if you do the sum of f of y's, minus 19 plus 19 is 0. If you do the sum of f of x, 10 plus 12 is 22. So far it looks like everything is good. And of course, ultimately, I would take a point here and I take some of the moments, like for example, like I would eliminate these two here. If I take some of the moments about this point here, right? So in other words, I would take 19 times 12 minus 10 times 12 minus 12 times 9. If that gives me 0, my analysis is perfect, okay? That's what I mean by taking the sum of the moments, and I should get 0. Now, what we're going to look at, of course, I tell you that, okay, calculate the displacement in inches. So therefore, I'm asking you for the displacements here. Okay, so if I want, I'm going to activate this, and I'm going to simply double click on this. And of course here, so I have, okay, so according to this, okay, I have X is positive, so I would show here positive. In this direction, it's 4.25 inches. Y is negative, very small displacement, very small, 0.02 inches. So that would be the displacements, okay? And, okay, where's the mouse? Now, if I want to see, of course, if I was designing this thing, what I wanted to see would be the forces in these members, okay? So basically, if I want to see the forces in these members, it all depends on what I want to see. Now, I personally, I would like to do, I like to do it this way. I would activate the members. If I want to see the force in this member here, I would do this, and it would give me all my MX, you know, my axial forces, my shear forces, my shear forces, my bending moment. That's how I like to look at my forces, because I like to see them that way. But if people want to see them the other way, like in other words, if you want to see your bending moments on the thing, well, here's your MX. If you want to see how this thing's going to actually bend, okay? So that means that this has a bending moment. This has no bending moment. This is the only member that has a bending moment. And once I've looked at my bending moment, then I would then look at my shear forces. And that gives me my shear forces. That means I have shear forces here, I have no shear forces there. And then ultimately, I would want to look at my axial forces, the ones that are acting along the length of the member, and that would be NZ. Apply, and there's are my axial forces. And therefore, this is negative, that means this member is in compression. This one is positive, that means this one's in tension. And of course, if I want to see this one, I would simply double click on it, and I should only have axial force here. It's a positive value. That means that it's got 45.35 kips in tension. So therefore, I would design that as a tension member. This one is in compression, and that's very hard to see. Like it's, you know, like I mean, I'm used to this, but when you guys look at this, it looks very, very messy, and that's why I don't like to look at axial force on the graph. I like to click on this. Oh, right away, this is like I would take this to be minus 33 kips, and that would be designed that as like a column. I would design exactly like a column. It's a compression member, and that's very important. And you look, no bending moment, no shears, and so on. And then if I want to see how the thing would deform, okay, how the thing deforms under the loads. If I want to get an idea how it deforms, I would take off my axial forces, and I would look for my deflections along the strong axis, apply, and of course, it shows me how this thing would deform. Now, if you find that that's a little too, you know, that's a little bit more reasonable, okay? So 4.25 millimeters deformation here. So therefore, look, this member has elongated by a whole inch. This member has compressed by a whole inch. You understand? It's amazing, okay? And this tells you this is deformation of your member, okay? Like I said, guys, a very powerful program. It can give you a lot of information that you need when you want to design something, and it can tell you whether the members are stiff enough, if you got too much displacement, if you got too much deflection, and so on and so on. And that's the only other, these are the only two examples, like these are the only two different types of structures I want to show you. That when you want to do a pin structure, it's very easy. Just make sure you know where you're releasing, what members are continuous, you know, and so on and so on. I mean, I can give you in the assignment that I gave you, You're going to have 2 of these examples to do in the assignment. And on top of that, I think I threw a whole 3 more that are going to be typical questions. So you're going to have 5 problems. Today, what I did is I let the assignment go at 11 o'clock instead of 11:30. You should have access to the assignment. And what I'm going to do for the rest of the lecture, I want you guys to start on the assignment right now, please. And if you have any questions, I'll be more than happy to share your screen, or I can do it on my screen. And I can help you with whatever problems you have. Okay. So I'm going to stop recording. So this way, and that should be it. Okay. So. Oh, where am I? So guys, go and get the assignment. I can't seem to find the. Okay. Okay. So is everybody good? Do you have access to the assignment? Can somebody give me a heads up, please? Let me know what's happening.
Yeah, we got the assignment.
Okay. So there you go. Okay. So that's no good. So where are you guys? There we are. Okay. Oh, stop sharing. Okay, so so you get some extra time to work on your assignment right now. Like the assignment is still due by 4 o'clock this afternoon. So guys, and like I said, guys, don't do snapshots. Make sketches. Start getting into the because I'm not going to take any snapshots on the test. So start learning how to most of you are doing it. Some of you are still taking snapshots of what you get from ADA. If you do that on the test, I will give you 0 for it. Okay, because you need to be able to take the information from the program and somehow transcribe it into your notes or whatever. And therefore, I want you to definitely make sketches and provide the information as clearly as possible. And hopefully,